And welcome to this week's statistics seminar. This week we have Dr. Surya Tokdar from the Duke University Department of Statistical Science, and his core research interest revolves around nonparametric Bayesian analysis of regression and density estimation problems. So today he would talk about something on the joint quantile regression under spatial dependency. So let's welcome our speaker. Please go ahead, Dr. Tokdar.
Thanks, Yang. Thanks, Yang, for inviting me. I hope this was an in-person visit, but it's still good, and hopefully I'll come over and visit you guys sometime in the future. So this is a work jointly with my PhD student, Shu Chen, who's graduating. The work Shu and I have done is on the spatial dependency part of the joint quantile regression, and we are working on generally just thinking about dependency within the quantile regression framework, spatial or other kind of dependency. But what I'll do in this talk is I'll give quite a bit of an overview of just the joint quantile regression part as well, because I think that is a part of it is familiar to you, but there are other things about it. Maybe more of a perspective that could be new. Just to give it a thought about how to think about it in terms of as a modeling and analysis tool, how it fits into what we typically do. Sort of that overview would be one of my main sort of talking points, but we will sort of do that more and more in the context of spatial dependency as the talk goes along. So let me start with that idea of how you think about linear regression, but not in the usual way, but through quantiles. So this is something that kind of kickstarted my interest in this area. This data set on Atlantic tropical cyclones. What you're seeing here is our tropical cyclones between 1981 and 2006. Every dot represents one cyclone. We are measuring its maximum strength, measured by maximum sustained wind speed for at least a minute, measured in knots, and the year of the cyclone on the x-axis. So a typical regression analysis, of course, would be done through what we have in this red line here. That's the mean regression line. And you would worry about certain things like outliers. Here is a dot, that's an actual dot, that's an outlier in the year of 1988, I think. And some issues about heteroscedasticity, that it doesn't look like a Gaussian noise around it. So if you wanted to be a little more robust, you could do the median regression, which is the green line. And if you look at the estimates, that shows a little bit of a more modest estimate of what the slope of that line is. So typically, this is what you do if you're trying to answer the question. What we're sort of seeing here is asking the question, are tropical cyclones getting stronger over time? So it's sort of, as you can imagine, it's related to the question of whether sort of this kind of disruptive climate events are becoming more and more volatile and more sort of strengthened over time, linked with global warming and climate crisis and everything. But once you have done the median regression, you realize that you don't have to stay put there, because clearly if you're interested in tropical cyclones or extreme weather events like this, you are more interested in the stronger side of that distribution. So you might say, instead of looking at the median line, I could think about the 90th percentile of the strength distribution, so storm strength distribution. I'll look at the 90th percentile and try to assess whether that 90th percentile has been shifting upward with time. And that's this blue line, which is a 90th percentile regression. It is, we'll see in a minute. This is done in a very similar way to the median regression with some tweaks done to it. It does produce a lot a much sort of steeper slope for that line, but also with wider standard errors. And that's a feature of quantile regression or this kind of analysis. The more you move toward the tails, the less data you have, and that uncertainty that comes with making inference about tails of a distribution is something that is a fundamental question in quantile regression, which would play a big role in what we do as well. So keep this picture in mind that it's not just an issue of being more robust than mean regression, but quantile regression is a legitimate, is a bona fide tool for scientific investigation in this kind of applications where you might care more about tails than the central part of the distribution. So here is the sort of a basic comparison between the mean regression and quantile regression, median being a special case of the quantile regression. So what you do is you change the conditional mean formulation by a conditional quantile formulation. And this is saying, as we just saw, that you're saying that given a quantile level, so let's say the 90th percentile level, you're modeling, and this is not exactly a model, but you're specifying that the 90th percentile is moving in your predictors or changing in your predictors, which was time in our example, but could be something else or a vector of predictors, is a line or a linear hyperplane in your predictors. So it's just a specification for one given percentile or one given quantile level. The estimation proceeds much like least squares estimation, but you need to use a different loss function. And if you look at this, then you'd see that when you're interested in the median, which would take that tau to be 0.5, this is just the absolute deviation loss function. You can ignore that. It's exactly, but you can rewrite this as the absolute value of the residual. But if you're interested in something non-central, if tau was small or closer to 1, then it's still two straight lines joined at 0, but the slopes of those two straight lines are going to be 1 minus tau and tau, or rather negative 1 minus tau and tau. This example is for tau equal to 0.9. So that's the only change you do to the loss function. Then you minimize your total loss in this loss function called the check loss. And you can do that by linear programming, the efficient linear programming, and then standard error. I mean, there is an asymptotic normal theory on the estimated parameters under that check loss function. Relates closely to M estimation, Huber's estimation. And then you could estimate the standard errors of those estimates using different techniques, but mostly what people do is they use bootstrap. And so you have the whole machinery ready to go in the quantile regression, mirroring what you could have done with mean regression. Now, what happens in reality is that you never stop at one quantile level. You never know exactly which quantile level to work with, particularly if you're not just focusing on the median. Median is sort of a special choice. You're interested in the central relationship, you go for that. But if you're trying to probe the tails or one of the two tails, there is no one particular magic value that represents the whole tail. So what you see in reality is something like this. You see that you see results or analysis that present quantile regression that have been carried out with many, many quantile levels of interest. So I'm sort of, I mean, I have been putting this in sort of this kind of box that people reserve for theorems. And I think this is sort of a real world theorem that nobody analyzes a single quantile level, generally speaking, of course. And in terms of inference people draw or this kind of sort of evidence people quantify, this is a very typical thing you would see. So so this is still going on with the tropical cyclone example in the North Atlantic. what we see here is a table with number of different, 5 different choices of the quantile level, probing the right tail. You're looking at the strongest hurricanes or the extreme distribution of strength. And you report here, what you're reporting here is the p-value, that the slope is 0 against its, I think it's one-sided. It's positive. You'd see that the p-values are quite different. For example, if you just compare the 0.9 versus the 0.95, they are entirely, they give a very different picture. This could, if you think about this, this could be a bit of an issue because, so what is happening, first of all, is that you have moved to the tails. Your uncertainty is great, but what is going on in this table is that this 5 columns of numbers that are reported came from 5 different analyses. So these are separate analysis of the same data for these 5 different quantile levels. There is no reconciliation between those. One of the issues that people see when no reconciliation is done is that you estimate the 90th percentile line here, and then your 95th percentile line at some point crosses it and goes down below, which of course is something that should never happen if you were to believe in the mathematical theory of probability. But if you're estimating lines separately, there is no guarantee that the 95th line is going to be above the 90th line. So that's taken as the embarrassing problem of quantile crossing. That's not always very apparent. But what still goes on is that since there is no reconciliation, and since there is great uncertainty in the tails, the standard error estimates change rapidly. They're very volatile. As you slightly change your quantile level, based on whether or not a point fell on that line, your standard error estimates are going to be very different, which is what I've tried to highlight here. That very, very different standard error estimates, which feed into giving you very different quantification of uncertainty in terms of p-value calculations like this. It could potentially lead to cherry picking. If you're trying to make a point that hurricanes are getting stronger over time, you could work with a certain quantile level to make that point. If you wanted to make the opposite point, you could work with another quantile level to say there is no evidence. It's just overall, I think, a bit unpleasant that these analyses are done separately and there is no reconciliation, and it leads to such widely different inference based on slight variations in the chosen quantile level. So what we have been trying to do is for many years now is to get into this question of how do you estimate quantile lines jointly. So our goal is to sort of present a picture like this, but estimate these lines together, and not just this sort of sparse collection of lines, but for every quantile level, estimate a line, all of these lines together, and present our inference about the slopes or whatever else you might be interested in jointly from one single analysis of the data, staying within the boundaries of probabilistic reasoning. So that's the real pursuit. And what we do is that we start with that model. So what we're doing is not for a fixed quantile level, but for all quantile levels in our in the range, between 0 and 1, we specify that model. So this is a joint specification, and that's a real difference from the standard quantile regression literature, where it's taken to be a single one. And there are some interesting debates about whether you should do it at a single level or all levels together. So of course, now your model parameters are function valued. The intercept parameter beta 0 is a function of the quantile level. Your slope parameters are functions. There are p-many functions hidden here. So each predictor has its slope function, again, a function of the quantile level. But this is not a model yet for quantiles until you have put down this constraint that your quantile planes are well ordered. I've written this slightly differently here in this dot notation, simply your beta dot 0 tau is the derivative of beta 0 tau with respect to tau. So I'm going to use that notation, the dot notation, to denote derivatives. If quantile lines are well ordered, and if your quantile lines are strictly well ordered, they are strictly increasing in a smooth way, then if they're strictly increasing, then they have to be smooth, because that means your conditional density is absolutely, conditional distribution is absolutely continuous. In that case, you could represent the well ordering condition by saying that the derivative is strictly positive. So once you put this constraint in for every quantile level tau at every value of the predictor vector in a given domain, then these two together has given a full model for your data. Then it is a model specification. The joint formulation is important to view this as a model. This is a point that sometimes, I mean, it's missed in quantile regression literature. And so let me stress on that point a little bit more. So under that two specification, where you're saying that you have this quantiles given by those hyperplanes, and the hyperplanes are strictly ordered, you can think of it as a fully generative model by writing it as an equation. So this is I mean, take this as a counterpart to what you would typically have. And let me write it this way: beta 0 plus xi transpose b plus epsilon I. Right. Let me make this a little more. Sigma epsilon I. Epsilon i's, let's say, follows normal 0, 1. That would be a standard normal linear regression model. So it's the counterpart of this that's given by this equation. So where is the noise now? The noise is not a normal additive noise. So it's not something that you're adding to a mean line. It's a noisy quantile level, the UIs that go inside your parameter value, the same UI, drawn from a uniform 0, 1 distribution. So what you're saying is that you have this template of hyperplanes, well ordered, fixed in place. How do I generate data y given x? Given an x, I generate a UI which is drawn from uniform, independent of x and independent of other observation units. And then I plug in and I look for that plane. The UI is a quantile level, a random quantile level. Look at that plane. Look at where in that plane the xi values takes you to, and that's your yi. So this is a generative model, and to see how this one fits into that, it's not too complicated to see. So what if you take your intercept parameter beta 0 tau as b0 plus sigma times the inverse CDF of the standard normal distribution. And if you take your beta tau, the slope parameters, to be constant in tau, equal to the vector b, then you get back this model. So the normal regression, mean regression is a special case. This is very simple. This is just saying that if you want to generate a random variable x having some distribution, or let me write it y. If you want to have y generated from, let's say, f of y given x, then all you do is plug in the inverse CDF formula, f inverse at a uniform given x. And the inverse of the CDF is precisely the quantile function. So that's all that is going on there, just the inverse CDF function. I'll pause here just a minute to see if this idea is clear, because this is sort of the mathematically very trivial, but conceptually was quite important for us to see and sort of talk about. And the rest of the work is based on this interpretation of the quantile regression model.
So can you explain a little bit more about the error, how the error add into the model? Because I'm not really following that part.
How the error is getting into the model?
Yes.
Right. So the idea here is if you go back to this figure here, and imagine I have a more dense version of those lines, one line for every quantile level between 0 and tau. Then what you're doing is, let's say this is the x value for which you want to generate a y. So this is the cross section of the x values. You generate a uniform random variable, right? And each line here corresponds to a quantile level. Let's say tau equal to 0.1 here, tau equal to 0.5 here, and so on. And then you find out, let's say your u turns out to be 0.23. Then you find out, where is my 0.23 line? That's going to go somewhere here, maybe. And then your y value is just this dot right here. So, and this is exactly the same thing you would be doing if you were in a linear regression with normal error context. So what I showed you here in this sort of quick derivation, when you have this sort of structure, let me just make some space here. So what goes on here is that this is your mean and the median line, which is given by y equal to b0 plus b transpose x. And then every quantile line is parallel to it. And their spacing, of course, depends on the spacing of the standard normal quantiles. All right. So what does additive error do to your model? You say that, okay, here is my x. So this is the expected value. I'm going to add an additive error to that. I get some epsilon I, and my point lives here, and this is epsilon I, right? So here also you are doing a choice of the plane on which to land, but the planes in the normal median case are represented by their constant distance from the mean line, because all the lines are parallel. So the distance between any two lines is constant. They don't change over the predictor. So you can represent your planes by the distance from the mean, and your residual is just a random choice of the line through the distance. But in what we are dealing with in quantile regression more generally, if the planes are not parallel to each other, you don't have to worry about it. You can still just go on thinking about indexing them through their corresponding quantile levels, and you choose a random quantile level and land on that line. Does that make sense?
Yeah, that explains a lot. Thank you.
Okay, good. All right, so what we once we start from here, so let's think about how do we unpack the non-crossing condition, which is the derivative condition we saw 2 slides back, right here. How do we sort of unpack that in building a model, an estimation model for the parameters, the p+1 function parameters now, the one-intercept and p-many slope functions that I have to estimate. This is, in general, not an easy problem, and that has been one of the reasons that for about 40 years, quantile regression hadn't seen that kind of effort sort of being fruitful. It's been mostly stuck with single quantile formulations. So let me sort of do that with a figure. So let's just think about 2 planes, or in this case, I'll take X to be one-dimensional, just to two lines. And we'll think about the non-crossing condition. When you think about non-crossing condition, you need to worry about non-crossing over a domain, over a particular range of values. Because if you want things to be indefinitely non-crossing, they have to be invariably parallel. Over two lines, two planes are non-crossing over an infinite space if they're parallel over that space. So if you're thinking about non-crossing and yet not necessarily parallel structures, then you have to have a bounded domain over which you want to enforce the non-crossing condition. And you can argue that if two planes are non-crossing over a set, then they are non-crossing over the convex hull of that set. So the non-crossing condition essentially needs to be done over a bounded convex set. In one dimension, that's just a bounded interval. We're going to make it sort of translate the domain so that 0 becomes an interior point of the domain for X, over which we're going to enforce this condition. So what is going on here is that this is where I expect my predictor variable to land. And this is the space over which I want the non-crossing condition to be satisfied. So we're just thinking about how to mathematically represent the non-crossing condition in a way that is more suitable towards statistical modeling. The derivative condition is nice mathematical expression, but that's no good for probabilistic modeling. Just two lines right now. I'll take the first line to have slope 0 and intercept 0. So it's right on this red line here that is just on the x-axis here. So I'm going to bring in another line and think about this blue line is something that is variable. It has a departure in the intercept given by this change in the intercept and this change in the slope. Those are the things I can control. So I can move the line up and down. I can tilt the line left and right. And I want to know what are my boundaries for those two quantities so that the blue line always within that domain stays above the red line. Sorry, was there a question? So to get a geometric interpretation of that, let's just first start out with how in this picture I can represent this these two quantities as sort of some geometric measurements. And that's done here. Your intercept is simply how much you have lifted the blue line from the red line at 0. So that's just this, this distance is delta beta 0. The slope has an interesting one. You draw a perpendicular to the blue line. This is the green line here. That's the perpendicular. And you go 1 unit up from here to here. That's 1 unit. And you look at how far the top of the perpendicular is from that point. So this length is precisely delta, the change in the slope parameter. In terms of the change in the intercept, any positive change will do. The blue, I mean, you have at least at 0, the blue line would be above the red line if the change in the intercept is positive. So we can do that. So what we would think about is sort of fixing a shift in at the center, and then think about just tilting the blue line. How much can I tilt given an upward, a vertical shift, and still not touch the red line down below? But to see that, just think about this. This is the range within which the blue line can move, staying hinged here, and still not touch or cross the red line, cross down the red line. Correspondingly, this would be the range for this top part. And if you think about what this is, it's a very simple geometric argument that the total sort of range for delta beta could be starting from 0 anywhere up to this number, which depends on two things: how much lift you have at the center and how far the domain extends to the direction of the tilt. are the direction opposite to the tilt. Here we're thinking about a positive delta, so we're looking at direction in the negative side. This is where the blue line tilts toward the red line. And it's just the ratio of that. The lift versus the radius in the opposite direction. That's all. So that gives a geometric interpretation of that. And if you're tilting the other way, if you're looking at a line that went something like this, you'd of course have to sort of measure it in this direction, but it's the same argument going for that one. So what we have, and let me just write down what we had there in this, is that your change in the slope. And if you are in high dimensional, this would be a vector, this would be a gradient vector. So what you'll have to have is that the length of that thing needs to be less than equal to your lift, your vertical lift at 0, divided by how far the space extends in the other direction. So what we had there, if we just sort of went with that, it would be the radius in the opposite direction. So I'll sort of write it in this way: radius opposite the direction of the slope. Right. So this is to match exactly with this formula here: lift over extension in the opposite direction. Right. So now what we have is a characterization theorem, which says that any stack of hyperplanes over a domain X that is bounded and convex and has 0 as an interior point can be represented in this way. So any stack of hyperplanes, it's a necessary and sufficient conditions for stack of hyperplanes over such a space to be correctly ordered in tau if and only if this happens, exactly what I wrote there. Here is a more fancy way of writing that same thing: the radius opposite to the direction of the slope. Okay, so that's a characterization theorem. It takes us one step toward a statistical modeling, and then there is this one that really opens it up. So we're still working with that idea that we need. Now, writing in terms of derivatives, beta dot, the slope gradient in norm needs to be less than or equal to the intercept intercept derivative, it's a scalar function, over how far the space extends opposite the direction of beta dot. So that's the condition we're trying to satisfy. So how can we model that? We start with a vector v that the norm doesn't matter. What we care about is the direction of that. The moment we have the direction, here is the radius opposite the direction of that vector. And what this term does in here is just gives it a norm that's between 0 and 1. That's all. And those are the two things we need: the norm being bounded and the radius in the opposite direction. So this is an exact capturing of that condition, and this is necessary and sufficient. So if you have a stack of hyperplanes which are correctly ordered, you can find the function v for which this happens. On the other hand, if you start with the function v and you define your slopes in this particular way, then you do have a stack of hyperplanes that are correctly ordered. So here is a sort of a picturization of how this is going to be implemented in statistical modeling. So the idea is you start out with an anchoring hyperplane. Let's say you anchor it at tau equal to, so this one corresponds to the median line. So tau is 0.5. So you start with there, and then you build your other hyperplanes up and down based on this derivative characterization that we just saw. So the first thing that's going to happen is that your vertical lifts at the center is going to be given by the derivative of the beta 0 dot. The intercept function's derivative gives you the vertical shifts here at the center. Now you think about putting lines there and tilting them relative to the blue line that you started out with. Let's start out with no tilts. So they're all parallel with the blue line. So this would be if all the slopes were 0. But I can change that. And these green little arrows give you the magnitude of the slope in either direction. In this particular case, the space extends more to the right than to the left. So what you have is that you can shift things a bit more upward here. But if you're shifting downward, which means you're shifting this line this way, then you have a greater chance of touching the line below. So there is less room on downward lines. But these are the boundaries that we get from that same condition, beta 0 dot tau, over the possible direction in which you can go. And here are only two directions. One is r plus and r or r minus. So what you need to do now is to think about what you want your slopes to be within your boundaries, within your bounds that you have. Those are the green dots here. I've chosen the slopes, positive and negative. This one is positively sloped. It would mean it would tilt even more upward relative to the blue line. These are on the other side, so this would also loop upward. So let's just see what the lines look like. So given those choices, these are the other lines you have. So now imagine doing this on a continuum, no gaps. So for every tau between 0 and 1, that's how we build our model. And that's exactly here. So you start with the hyperplane, the quantile plane at an anchoring value. This could be your 0.5 value. The hyperplane with parameters gamma 0, gamma at the center. You build your other hyperplanes up and below, above and below that anchoring one, based on a shifting function beta 0 dot, which you can define based on certain considerations of a parametric model embedded as a center of your model. And then once you have done the vertical shifts at the center, your slopes can be done based on that characterization we saw earlier, based on some new functions, p many additional functions here that are completely constraint free. There's zero constraint on this p functions. As long as you use this transformation, you are satisfying the non-crossing condition.
So, question, please.
Go on.
But your modeling would depend upon the choice of the domain. So, for example, if your domain is time, and in the example that you gave at the beginning of your talk, you might be interested between 1980 and say 2000, but if you increase your domain a little bit, like because you want to forecast, then the domain would potentially change and that would change the estimator. Does that matter?
It does. It does matter hugely in the application. And when you're specifying, so we're talking about linear quantile regression models, but linear in what is a good question there too. So the example I showed you was linear in time. If you want linear in time quantile regression, and you want to forecast forward, let's say we wanted to forecast until 2050, then the domain extends so much that, of course, to satisfy non-crossing, your lines are going to look more and more parallel to each other, right? Because you have extended that. So you have to be careful about what you're modeling, what kind of predictor effects you capture. You could, if sounds like something that is very restrictive, then there are two ways to think about it. If you really believe in a linear growth, then you cannot, over a very long time, over infinity, you cannot think about non-parallel growths of different parts of the distribution. There are certain models that go sort of inside out, that sort of center out ray-like of modeling that can happen. Everything is moving away from each other. Another way to think about it is that you really want to capture monotone transformation. So you don't have to be exactly linear. You could sort of have some shape flexibility by some nonlinear transformations of time put into that. And then you could extend and allow your model to capture interesting structures over a larger period of time. But what you choose your domain to be is going to be an extremely important thing in any quantile regression, not that we are formalizing what is already done, but what is done is going to be affected by choice of that domain.
Thank you very much. Thank you.
All right. So once you've set up this model, then it's a simple thing. Our model has become essentially constraint-free. We have one function that needs to be this intercept function that has to be increasing. The other functions are based on constraint-free functions. We can write down a log likelihood function because ours is a fully generative model. It's the same inverse CDF formula we saw, the generative model formula, the density derived from it coming in here. You can write down the log likelihood function. The likelihood score calculation, Bayesian MCMC, they have a lot more detail that I'm going to omit. You can do that. And typically what you
ask a question, in the last slide, you said that as the time increases, like say we are predicting for a long horizon, then the lines are going to be parallel to each other gradually. So can you just give us an idea, like how long can we predict, like reasonably, how depending on a situation?
So I'll refer you to that paper instead of answering that here. That idea, I think it's probably at the end of this too. So where we started out from, and just take a look at this paper because we answered that question specifically. If we extend our analysis to 2010, the data was until 2006 at that point. What do we infer about the growth rate of the different parts of the hurricane strength distribution? What happens if you extend that to 2020? So you start getting more and more conservative estimates because now your lines are going to be restricted somewhat. But one of the sort of major conclusions of that paper was that no matter, within that reasonable range, you do see a strictly positive increase of hurricane strengths over time. So I think that would probably answer. Just take a look at that. It's a consideration in any quantile regression. Quantile regression is more in the regression in general. Always parametric regression in general is about interpolation rather than extrapolation. Whenever you're trying to extrapolate based on a regression model, you should be very, very careful. Quantile regression just makes it very explicit.
Thank you.
All right, so I'm going to just go to, sorry. So this is the typical kind of stuff you'd see in terms of your estimates. You see this estimates of the intercept function, estimate of the slope functions, and being a Bayesian model, we jointly estimate the credible intervals for each function, sort of pointwise credible bands for all these functions. One of the things that we see repeatedly, and this is one of our motivations, is that we get much tighter credible intervals with nearly as good a coverage as the nominal ones. The 95% credible intervals have close to 95% frequentist coverage, but they're much, much tighter than the bootstrap-based confidence intervals that you get from the point-by-point estimation. And that's partly, again, going back to that question that tails have less data. The bootstraps are okay, but they don't kick in very well. So you do end up estimating standard errors to be much larger than it needs to be. All right, let me move over just to talk about briefly the adjustments for correlation because we're a little late. The main idea here is the following, that let's say we are now in a situation where your observation units are geolocated, so you know the exact spatial location of unit I. Our model doesn't quite change. We write down the same generative model as before, but we can now think about this noisy quantile level as also as a spatial process. They could be spatially dependent. The noise is spatially dependent. And what we have done here is we have expressed it through this copula process. The main idea really here is that our generative model says that you need this, and it also says that that marginally the UIs need to be uniform 0, 1. That's all it needs. It doesn't say that UIs have to be independent of one another. So if you want to model dependence between UIs and you want them marginally to be uniform, what do? You use copulas. And if you want spatial correlation, then use a spatial copula. This is a Gaussian spatial copula. You start with some Gaussian process, smooth Gaussian process, plus a nugget or a noise rather. And then so that the overall variance is 1, and then do a normal CDF transform. So U becomes a copula process with margins being distributed uniform 0, 1. That's the extension, what that we pursue here. The log likelihood score changes very slightly, not much. You have the old one that we had before. The only new piece is the contribution of the copula density on the observed data points. And that's a simple change to the likelihood function calculations, a simple change to the Bayesian machinery, doesn't require anything more. You have some parameters now that come from the copula part, so you have to update those. You have to include them in your Markov chain sampling. But it's really a very simple, conceptually at least, very simple change. So we get the whole machinery going on there. I'll skip this point a little bit. Here, one of the things it allows us to do, because we have modeled noisy quantile levels, is that it allows us to do quantile triggering. So given what you have observed in your data, you could now give me a new location S star and some new predictor value X star there, and you can ask me, what is the quantile function going to be there? Conditional quantile function going to be there, given what I've observed. What this is doing is really triggering or predicting your observations, your batch of observations at unmeasured spatial locations. And that's what this does. This follows very closely the triggering mechanism. It uses a lot of those formulas, but of course has the quantile regression on top of that. This ability to do this, to predict quantiles at new locations given what you had, model noise correlation, all of this happens because we have this generative model. Without that, none of this could have been possible. So the generative model formulation is not just aesthetically pleasing or just about standard error, better estimation of standard errors or credible bands. It is a question of being able to extend the quantile regression model fruitfully to a much broader field of applications with different structures that you want to add to your model, like dependence between, spatial dependence between observation units. I'm going to sort of go over a little bit of this. I'll try to stop in a couple of minutes. So first, you run a lot of simulation studies. You get much better estimates of the quantile regression parameters, the intercept and slope parameters, when you account for spatial correlation this way than when you don't account for them. And we have tested this both when our spatial noise model is correctly specified and when it is misspecified. And we have seen that you can, if the degree of correlation as it changes in a simulation study, you can change it. Our model estimates also adapt to that change. It can capture that change. And indicate whether it's nearly independent versus it's very highly correlated across space. It gives a much improved triggering accuracy, which is extremely relevant both from the perspective of making this useful in forecasting or imputing missing data in missing locations, unmeasured locations, but also to think about assessing model accuracy. That if you want to think about whether the model fitted the data well or not, you can hold out some data, do the triggering, get the quantiles at the held out locations, and then compare the entire quantile function with the observations. And that gives a more comprehensive model assessment. The two things that we sort of mentioned here are really important from an application perspective. What I showed you earlier was a Gaussian spatial copula, which does not take into account the possibility of tail dependence. Our model for the quantile regression allows for heavy tails. And if the Gaussian coupler doesn't care about tail dependence, but if you change to a spatial T coupler, then it can capture heavy tail dependence. In that context comes the really, really important question: can you even compare these models? Not heavy-tailed quantile regression model with Gaussian coupler versus a heavy-tailed quantile regression model with Gaussian coupler versus a heavy-tailed model with a spatial coupler that can capture tail dependence. Can you assess which model fits your data best? Which one do you need? And we have done some extensive work with WAIC. I mean, starting out with how do you calculate WAIC in this kind of dependent situation, but then extensive numerical analysis of how well it aligns with held out data prediction kind of assessment of model fit. And we've seen that this is really a good tool to just capture in one number how well a model fits our data in this context. As an example, I'll end with this one. This is analyzing air quality and the particulate matter 2.5 PM 2.5 analysis with data coming from 339 weather stations in the US. We're looking at average daily PM 2.5 concentration. There are several covariates that we are interested in. And this is the model comparison that is important here. In this particular one, it says there is spatial dependence because the ordinary, our old joint quantile regression model without spatial dependence performs much poorly than the two versions that uses quantile spatial dependence, but doesn't show any heavy tail. And that's because we're taking that average daily value. Maybe that's why there is no heavy tails. Heavy tail or tail dependence. I'll skip this, but we also did another analysis with wildfire risk assessment. And in that one particular, we see that the WAIC is the smallest and by a margin for the case where we account for heavy tails in the distribution as well as tail dependence. So it's there, both are present. And again, we cross-validate this against held out assessment of model fit, and they also present the same picture. So I'm going to sort of stop here, just leave with this, just briefly touch upon that again. These are the kind of inference you get, inference on slope, inference on intercept. We have compared this against a standard Bayesian spatial random effects model, which are shown in these gray bands, which doesn't account for quantile variation. It's a model for the mean with a spatial random effects added to it. And you can see that there is some value in this quantile regression. We captured this sort of effects of certain covariates that are present in certain parts of the distribution, but not everywhere. So particularly these two covariates, one is the urban land use and the other one is local emission of PM 2.5. Both have strong heterogeneous effect. They don't have much effect in the median, but one has a strong effect. Urban land use has a strong effect on the lower quantiles, and the local emission has a strong effect on the upper quantiles. For example, if you increase local emission by 1 standard deviation, that causes a 7% increase in the 95th percentile of PM 2.5. So these are kind of questions that you could not have answered without quantile regression that you could do now thanks to this kind of generative model and its extension to the dependent case. All right, I'll stop here with this thing that this is how I sort of view some sort of quantile regression as a compromise, as a really good application motivated compromise between a very restricted linear regression, which is not just restricted because it's not robust, but because it doesn't allow you to probe those interesting questions about the tails being different than the center. But it's much more structured, much easier to fit and interpret than a fully non-parametric density estimation that you could have also worked with. All right, I'm going to stop here. Thanks.
Okay, thank you very much for a very nice talk. We will have time to take a couple of questions. So if you have questions, please just go ahead and unmute yourself.
Can I ask a question?
Yeah, please go ahead.
Thank you, Dr. Tokdar, for the very nice talk. I have a question regarding the uncertainty quantification. I mean, for the credible intervals for the beta. So it is known that for the Bayesian quantile regression based on asymmetric Laplace error, the credible interval obtained from that model is somehow deviates from the frequentist confidence interval as n increases. So is it something similar happens in the like a uniform error model in this presentation?
So, I mean, no, I mean, that was really the crux of what we kind of did earlier and then have gone back again and again. What we've seen empirically at this point, no theoretical sort of result on coverage of credible bands yet, but empirically, our estimates are much more faithful to the original Poincare-Bessette kind of estimates, both in terms of the estimated values and the shapes of the credible interval. So the uncertain quantification, they follow very sort of similar patterns, but particularly when you're dealing with in this kind of multiple covariates that are positively or that are partially correlated with each other, not perfectly, but still correlated with each other. These are the situations where the Poincare-Bessette kind of formulation with a bootstrap-based standard errors become very large and the bands are wider. And ours give sort of a smoothed out version of it, but these are still wider than the ones you would get under asymmetric Laplace distribution. And one of the problems that we had noticed early in using ALD was that as it might happen that as you get closer to one of the two endpoints, tau near 0 or tau near 1, the ALD credible bands, Bayesian credible bands, can start collapsing back to 0. They not only, I mean, are bad, they're very bad in the sense that where your uncertainty should be maximum, they're pointing to very little uncertainty. That happens partly because the ALD is sensitive to outliers because of its exponential tails. And we always see, as sort of in the sort of evident in the picture here, is that that's something that doesn't happen here because this truly, it does, I mean, it does smoothing, right? At the heart of it, it's smoothing. And smoothing is much more inherently sensitive to local uncertainty than being influenced by global outliers. So this captures the local uncertainty in a more appropriate way, often agreeing with the Poincare-Bessette bands more closely than what you see in this picture. Particularly if you have one covariate, the bands are very similar. But when you have multiple covariates with some positive correlation, that's where the KB bands start behaving weirdly.
Thank you.
Can I ask a quick question?
Yeah, sure.
Yeah. It's rather comments. So if you consider restricted linear quantile regressions, yes, that's true that if you want to have non-crossing quantile indefinitely, you have to have all the hyperplane to be parallel to each other. But I'm just wondering if you extend that to nonlinear regression, nonlinear quantile regressions, then that's potentially more flexible, right? You don't have, even if you require the quantiles to be non-crossing across the entire domain, you don't necessarily have to restrict your attention just to parallel curves or surface in that case. But I guess in terms of deriving this constraint that you have, very nice constraint you have in your theorem, perhaps it's much harder in that case. But on the other hand, maybe if you can do, let's say if you do basis expansions of your covariates and then derive, basically using the same constraint you have here on the expanded basis, would that correspond to some very flexible quantile surface that not necessarily parallel to each other, but at the same time also do not cross each other.
Right. I mean, it's. So I just wanted to show you this because this is an example where, I mean, you have one covariate. This is a motorcycle data, just a toy example, but it illustrates the point. you have one predictor, one covariate, but 15 predictors which are nonlinear B-spline transforms of time, which is the covariate here. And so this model is a linear model on that 15-dimensional space, then sort of revisualized in the one-dimensional. So you can do that, and it really depends on how you're doing the transformations, and where you place 0 in your space is actually an important question, because if you even think about our model. Let me see if I can have some space here. I just ignore these other pictures here. What I said is that, is that you have 0 somewhere, and this is your space. Let's say this is the space I do. I take 0 much closer to my left point than my R point, than my right point, all right? So when you have this, since your 0 is very close to your leftmost point, it allows your, you start getting lines that could flare out like this, right? And if you have those, they go on for infinity. So those lines are I mean, those are already included in our model space. By taking, if you wanted to do a real sort of forecasting analysis starting from now, forever onward, then you might even consider placing 0 exactly on that right boundary, and then keep taking your R plus go to infinity, because that becomes a vacuous thing, because you're never going to consider those ones. It's how close your R minus is going to influence in your model. So you can make this arbitrarily go on in one direction, which could make more sense in forecasting, whether it's you do it linear or transformed linear, which would look nonlinear in the original space, is not, I mean, that's not a restriction, but it's really where you can move in one direction. That is possible. But the consideration of the domain, the consideration of the interior point, the 0 point, what does the intercept mean in the context? These questions become much more important to think about in quantile regression. They're there in general regression also, but they're not so sort of important to be nailed down in a lot of detail. But in quantile regression, these are modeling choices you are making.
All right. Thank you very much.
I really enjoyed your talk. Is it okay if I ask a question really quickly?
Yeah.
I guess we still have time for only one quick question. Yeah.
Oh, it's very short. Does the choice of the anchor point matter?
Good question. I think it does. And this sort of simple illustration kind of shows you by changing it, by moving it one way or the other, you can allow for your certain kinds of sort of structures in that stack of hyperplane that may not be allowed if the anchoring point, the anchor point, not 0 point, you're right. Okay, sorry, I got the question wrong, right. So the first hyperplane that you start out with, right? Is that what you're asking about?
Yeah, if you chose one, does it influence the others and then maybe change
not in a great way. We have done that, and this is generally robust to that construction, but it can have some impact. It's I mean, and not in the mathematical formulation of it, but as you can imagine, there is going to be a lot of prior specification that are going to be put on top of this. This is all our model parameters, and this functions. There are p+1 functions here. These are unconstrained, and then there is this function that is an increasing a diffeomorphism between 0, 1 to 0, 1. We model that too. The way one way to think about it is that given an anchor, so if you want to keep the models the same, you can map the anchor points correspondingly by mapping the priors on these functions. But if you keep your prior the same on these functions, but change your anchor point, then the model is slightly different. And if you change the anchor point by a lot, then the model could be quite different. That is a possibility. We have not done any extensive analysis of that, but my guess is your sort of prior centering is at a different place as you change the anchoring point. And as any Bayesian model does, this is going to shrink toward your prior beliefs. And so it'll have an impact.
So if you cared more about a different percentile, you might focus the anchor point there as opposed to the median.
If you, yeah, I think that would be, particularly if you had one tail that you were more interested in analyzing, you would do that. In particular, I mean, what we do when we have response data that is, say, just positive valued. So just modeling, for example, birth weight, or modeling some of this ecological variables. We use a model where the anchoring point is actually at 0, not at 0.5, but at 0. So we just we have the lower line, and then we build the model only upward, because that's what makes more sense in those applications.
Okay, perfect. Thank you.
Okay, I think that's pretty much it for today's seminar. Let's thank our speaker again, and I will see you guys next week.
Yeah, thank you very much. All right.
Bye.
Hope to see you in person soon.
Yeah, we'll do. Thanks, Yang, and thanks, everyone. Thanks, Yang.
Bye.